Hello everyone, my name is John Truckenbrot. I work at the Earth Observation Department at the Friedrich Schiller University in Jena in Germany. And together with a couple of colleagues, I've been developing a SAR tomography tutorial in the last couple of weeks, and this is what I'm going to show today. So actually, I'm going to jump straight over to the GitHub page, which is our main point of entry here for the tutorial. And here you can find actually the whole source code that we developed, and also installation instructions and further links to the data itself and to EO College. So this whole framework was developed in EO College. And so once you found this video now, you also have access to the other material. So that is theory, slides, PowerPoint presentation. That is, well, here the link to the GitHub page and also the test data, which you can download there. Okay, so the data that we're going to use today is airborne SAR data, synthetic aperture radar, acquired by DLR's FSAR sensor. And so we have a test data set over near Jena, also in the forest here at Trockenborn. And I can also show you a link here. So this is where we are, directly our test site, and Jena is here. So Trockenborn is to the southeast of Jena. And this is also a test site of our department where we do lots of studies. And this is also where we acquired the data for, to also use it for our own studies. So first of all, we want to start by installation. We want to get this tutorial running. It's all packed up into a Python package, so you don't have to worry about anything, any scripts or so on in the first beginning. You can basically just easily install it via command line. And I have also added installation instructions for Ubuntu, so a Linux system. So that should be easily also comparable to Debian, for example, if you're using that. And also Windows installation instructions here. And this is also what I'm going to show today. So I assume that most users are more familiar with Windows. And so this is also what I'm going to do here. And I have already installed everything that we need for today, but you can find installation instructions here. So we're going to use Anaconda. That's by far the most easiest way to get Python running under Windows, and Python we need for the tutorial. So you can install this, and please make sure to use the Python 3 version. This is what we need here. The tomography tutorial was developed for Python 3 and Python 2.7. It's still there, but it's not really so much developed anymore, and so the really support for it will drop out very soon. And once you've installed Python, then we further need the geodata abstraction library, GDAL in short, for the handling of geodata. And this is also one of the preliminary steps that we have to do before running the tutorial, that we install this package separately, and then we can install the tomography tutorial itself. So you also find a link here with Conda, which is Anaconda's installer. Pip is a similar one, so Conda is directly for Anaconda. You can use that to install GDAL. And once you've done that, we go further and just via this line install this tomography tutorial. So if you're interested in it, this installation via pip that we do here is possible because we also registered this package on PyPy. So this is the official Python packaging index. So basically a repository where all of the Python packages are listed. And so you can also, again, on this page here, find the command for installing the package. You find some information about the license, about author contact details, and also the same text as we just saw here on the GitHub page. Just generally makes it much easier to work with it. And yeah, once you've installed this, you have access to all the Python functions that we developed. You have some functionality also for displaying the data, and basically everything that we're going to explore in the next couple of minutes here with the tutorial and the Jupyter Notebook. And talking about that, the Jupyter Notebook is also part of this particular package. And so you can easily start it directly from the package directory. And before we go into the package itself, there is one more step that we need to do. We need to download the test data. So you can also find the link here, and you can also find it over EO College. So it's just a zip directory containing all those files that we are going to need for the processing of the tomography data. And so for the tutorial, we need to download that and unpack it to some local directory that we have access to. Okay, once that's done, there's only one more thing to do now. We are going to start the tutorial itself. And the tutorial itself is in the notebook is contained in the Python package, but we want to separate the Python package from your notebook. So we want to create a custom copy of this notebook. So in case, for example, in the future, we are going to develop some updates, some improvements of this package, and you are going to install the updates. If this tutorial is still contained in the Python package, it will be deleted and the new one will be downloaded. But if you have your custom one, where you've made some changes, maybe some improvements also, then you want to have a custom copy obviously, so you're independent of the package itself. And so therefore, there is a function that's just called start in this tutorial. And you call this with just start. You import the package, you call the function start, and here you provide a name of the notebook that you want to create. So it's just copying it from the package directory to that custom location. And the directory that you define here, if it doesn't exist yet, then it's also created automatically. So all the subdirectories also, they are directly created and the notebook copied. And so much for the talk. One more thing that's also interesting for more of the technical persons also, if you want to delve into the Python functions themselves, there's an API documentation, and there's also going to be a couple of links in the tutorial in the notebook, so you can also directly go to the API documentation, see what the function really is, what parameters it takes, what the output is, and also a link to the source code. Now, so far for the theoretical part, let's jump over to the actual work. And you see here in my start menu, I have the Anaconda prompt, and that's what we want to use. And just in case, I started in the administrator mode, and that just gives me a command line. And here I can now, access Python and do the coding. And so I just type in Python, I started here, and now I can go on. I want to import a function from the Tomography tutorial. That's the package that we just installed, and it's called start, just in the description on GitHub. So that worked. Everything seems to be installed well, and we can import everything. And now we are going to start this function. And for this, I have prepared a directory. So it's just called Tomography here. And it contains a data directory. So these are all the files that I've been talking about that you can download in a zip file. And it also contains a directory out already. And out here, these are just the files that we're going to produce now. I've just produced them earlier already because some of the processing steps, they take some time. So it's ready already, so I can just load them in. And in your case, if you want to do it, you cannot do it in parallel because it will be too fast, but afterwards you can do it for yourself. And so the directory here is D is the drive, and then Tomography. So I'm providing this here, D to Tomography / and then I just name it notebook, like that. That's already enough. As you can see here in GitHub, I also put the extension with .ipynb for IPython notebook. But if you don't provide that, it's also automatically created. So if you push enter now, you see the notebook is created here. It's copied from the package directory to that directory that I provided. And it's also automatically started in your browser. So in case you're not familiar so much with Jupyter, it's actually quite easy to get familiar with. You have here a panel for saving the notebook, adding extra boxes, deleting some boxes also. So for example, if I put a plus here, then it's just creating another box, and I can select whether that's code or whether that's markdown. So these description boxes here, that's markdown format. This is code box. And so you can play around with it and add some more lines, well, do whatever you want. It's basically an interactive Python script. And then for executing boxes, you have the run button here. I'm going to use that in a minute. And one more thing that's a bit more important. You see here on the top right, it says Python 3. So that's exactly what we want. It says it's a Python 3 kernel. So Python 3 is running in the background for executing the functions, everything. And you also see that dot here, that circle. And that's an indicator of whether the kernel is idle or whether it's working. You see here, it's idle. So nothing is being done because, well, we're not executing any function or so. But in a minute, if we are running some functions, you will see that the circle is going to be filled. So whenever you're wondering whether the kernel is still working or not, whether your function has been executed or not, just check on here on the circle and you will see. All right, so that was just some demo box. I'm going to delete this. And so now we are step by step executing all those different boxes and see what the result is. So you can either click the run button here. So, well, there's nothing really much to be executed. It's just a markdown text format. But with Python, then there's obviously something happening in the background. And so I don't want to be pushing this button every time here, the run button. So I'm just using a shortcut. I press Shift and Enter, and does the same thing. Box is executed, and so you can just Shift, Enter, and do it repeatedly and jump through all the boxes. Yeah. Now, that was just 2 markdown boxes. The first one with Python is now here. And it's just going to import some other packages that we are going to need. So OS is just for some system data path handling, NumPy for array computations, and matplotlib. That's an important one for us also for display, for visualization of the whole data. Shift Enter and done. So that worked. Import was successful. We go on further and Shift Enter again, and also all the tomography tutorial functions were imported, well, regularly, no problems at all. If there would be an error, you would also see that popping up here in the notebook directly. Again, here you also have a link to the GitHub repository, so you can always check back to see what's going on there. All right, next box up is the only one that we have to change, actually. Unless you really want to do some more exploration yourself, of course, later on. But this one is one we have to change because it gives us 2 variables here for an in directory where our data resides, the test data, and also an out path. So this directory that I already showed you early on where the data is going to be written to that we process here. So in my case here, D tomography, and so I'm going to change that here to D tomography data. That's this one here. And then further this output directory, also D tomography out. That's done. And then we have 2 more processing variables. One is multilook. So it's basically just a pixel smoothing factor for reducing noise. And this is the inversion height for the actual tomography that we're going to do. So for the moment, we just leave it like this. And the files that are going to be created throughout the tutorial will also have these 2 factors in their name. So you can see that here. So in my case, for example, here, it has a underscore ML10 in the name. So that's for multilook 10 factor. So that's the only variable that was needed for creating this file. For this file, on the other hand, you need both of them, so the multilook factor and also the inversion height. So in case you come back to the tutorial, want to change some of these factors and see what the result is in comparison, you just change the factors and the names are created automatically, so you don't have to worry about any file handling in the background. Makes it easier. That's the 2 directories, and we want to read the data from them now. And as you can see here, this out path that we define up here, it's also created automatically, so you don't have to worry about that either. And here we are going to use the function called list files from the tomography tutorial. And all it does is it scans a directory and lists all files in that directory that match a certain pattern that we supply. And that's the pattern here. In case you're not so familiar with this is a regular expression. I also put the link here for some more thorough explanation from Python. And it's basically just a pattern that matches file names. So in this case, a file that starts with SLC underscore followed by one-digit number between 0 and 9, another underscore, then a date acquired on October 13th, 2015, underscore, then L, because it's an L band. I was mentioning we are using the SAR DLR system here, and if you head on over to the page of the description, you see that this airborne sensor has 5 different bands, so different radar wavelengths, and we are using L band in this case. So that's the L in the name. And then you have underscore HV, which is just a radar polarization. So horizontal transmit of the electromagnetic waves scattered on the ground, some of it depolarized from horizontal polarization to vertical polarization, and some of the depolarized part is coming back to the sensor, and this is what we are going to acquire. So horizontal emit, vertical receive. And very similar to this, we have 2 more lines here. So that was the SLC data. Then we have phase data. I'm going to talk about that in a minute. And this is kappa zeta files. So that is the wave number files, all radar specific acquired by FSAR. Okay, so we're going to list these files, and to make sure that everything worked properly, that actually this function list files also found those files, we're going to add this line here and execute the box, and we see, okay, it's just giving us a printout of this SLC list. So in every line, just one of the file names, and you see here we have 9 files with this identifier from 0 to 8, and the rest is identical. So you see here the pattern above that we have here. And yeah, one more thing, this dollar in the end means just that is the end of the file. So nothing else is going to come after that in the name. So if you head on over to this directory where the data resides, and you see this SLC data, one SLC dataset contains of the image data itself, and then also another file that ends with the .htr, so header file, it's an NV format. And by saying here with the dollar, so after HV, the file name is supposed to end, we are only listing the image files themselves and not the header files. And same as we did here with the SLC list, we can certainly also do that with the phase list. Yeah. Okay, and so there's also some explanation of what exactly this data is here. So you can have a look at that, and also, of course, obviously always return back to the theory PowerPoint presentation and really get more into that. I'm not going to talk much about that today. All right, so we listed all our files. The system has found them. Let's stack them. So let's load the files into memory, stack them into one 3-dimensional array, and save them back to disk. That's what's going to happen here. And so the names of the files that we are creating here are SLC stack, phase stack, and this kappa zeta stack. And I'm executing this. It was quite fast because it's just reading them from the disk again. In your case, it might take a little longer, and you will find them here. So KZ stack, phase, SLC stack. These are the 3 files that we produced. And what it is basically, it's the 3-dimensional NumPy array that we created directly, this Python object directly written to disk. And you can also, in case this file already exists, then this function readdata is not going to create them new, it's just reading them from disk, unless you set this parameter override to true. Then it would delete this old file and write a new one. So it makes it just easier when you're coming back like me in a moment, that you just read the files from disk instead of producing them new all the time. All right, so what we have now is the SLC, phase, and Capazetta stacks. And if you want to know what this actually is, then you can just put SLC stack, print that, and you will see as a print type here numpy nd array. And the SLC stack dot shape will also give you the dimensions of that particular array. Yeah, so 3-dimensional array. All right. So now that we loaded the data into NumPy arrays, we have it in memory. We can work with it. We can also well display it, and that's what we're going to do first. And the next box here just gives you some plots of what the data actually is. And you can scroll through these files because, well, here we had several of them. So you can use the slider to slide through these individual files and see what it actually is. Well, the phase and the wave number are not so much meaningful. There's not so much to see. The SLC data for, well, the purpose of visualization, I converted the numbers because it's in complex format, so it has a real and imaginary part. And I just extracted the absolute number from that data and also scaled it logarithmically. So to have it in decibel values, I mean, and this is just much easier for display. It's much easier to look at, and in SAR data visualization, that's actually quite common practice. So if you scroll through the images here, you can see the SLC data. There's not so many differences here. You see some changes, but very marginal. And that's because, well, they show the same area and they are co-registered to each other. So they show exactly the same thing. The only difference is that these individual images are acquired from different viewing angles. So, well, that's the whole idea behind tomography, that you want to view your area on the ground, your volume information from a forest three-dimensionally by looking from different viewing angles. And so the bright area here to the right, that's the forest that we are observing. And I say to the right, it's not geographical coordinates, it's in slant range radar geometry. And so the actual image it's flipped and also rotated because, well, it's sort of aligned to the radar flight path, the orbit flight path. And the geocoding we're also going to do later. So for now, we just refer to left, right, top, bottom. And also here, so that is the forest. The darker area you see here, that's, well, pasture, grassland. You see here is a line of trees along a way through that pasture. And to the bottom left, you have a little village. It's called Trockenborn. I already showed you it later, so that's here. So you could rotate Google Earth, have the forest to the right and the village to the left, but you see still the line of trees is to the bottom, whereas in our case it's more to the top here because it's also flipped. All right, so now that we've familiarized ourselves with the data, let's jump on over to the first processing step. And this is the topographic phase removal. So what's that? As I said, we have complex data with our SLCs, so intensity and phase. And, well, the phase information contains different components. One of them is a phase change through topography, so height variations on the ground. Another phase contribution is that of the so-called flat earth effect. So a change of phase by increasing the distance to the sensor. And we are going to remove that effect from the data. And what's left is a phase component that displays the height variations above the topography. So for example, the trees. That was also very quick in my case, and we now have a normalized SLC stack, it's just called normalized stack, and you find it in your output directory then. So the next step is a bit more complex. It's the computation of the covariance matrix. So that is also very similar to what you would do in interferometry, that you take two image pairs acquired at a different time, different viewing angle. You then compute the coherence between these two images, so the, let's say, phase likeliness. And this coherence we are going to compute not between only two images, as you would do in regular interferometry, but between all 9 images that we have from the SLC data. And all those different combinations between all of these images, the coherence, we are going to say that in the covariance matrix. So that's going to be a big file. It's going to contain quite a bit. All right. So I execute that box and it's done. And you will find that here, the covariance matrix size roughly, say, 750 megabytes. And now that's done, we have everything to do the tomography itself. This step is called Kappan beamform inversion. And so we are executing this to get our final result, the one that we are going to explore in a minute. That is our actual tomography data set. So also very quick, if you're doing it yourself, you will find that this step takes quite some time. It's quite computationally expensive. And then here you will find that in the directory it's roughly the same size. Well, it's 650 MB, not quite as large. All right, so here we go. That's done. And here for the Kappan beamforming inversion, I also, just in the case as with the other processing steps, I put a link directly to the documentation here. So you can follow that link and you are directly referred to the documentation page of the tomography tutorial package. And so that gives you a bit of an insight, as I was mentioning earlier, what exactly is this function, what does it take as input, what comes out of it, and here the link to the source code. So you can follow that and have a direct display of the source code in the browser, and you have, well, a good overview of what's actually going on. One more thing that we need to do is normalization. We want to normalize this image by pixel, so it's a 3-dimensional array again. 2 dimensions for rows and columns, so, well, the area, and 1 dimension for actually the vertical profile of our tomography result. And the normalization, basically it's very similar to NDVI. And I head on over to the normalized documentation here, and here you see the equation for it. And this equation is going to be applied to each of the pixels throughout this vertical profile. And this again makes it easier to visualize. I compute this, and this is actually done by on the fly. I don't save the result here, but it shouldn't take too long. It's quite quick. Right, so the processing is done. Let's jump over to the visualization. And here you can actually already see some of the plots that are directly saved into the tutorial. Well, it's basically for the display on GitHub to have an idea what really the output of the tutorial is. So it's just a static plot. And we again now execute this, this tomography plot functionality here to have an individual plot that we can play with. So Shift Enter. And you see the plot is refreshed now. Well, except for one box, they're all empty. And now we have on the top here some options for, well, adjusting the plots. And before much further ado, I just click on the plot here. And you see we have a crosshair now here on this image. the coordinate that we clicked on right now. And to the right, you have the vertical profile of this carbon beamforming inversion. And you see here, it's from 70 to minus 70. So that's the parameter that we set up here, this inversion height. You have here the reflectivity. You see the forest has a higher reflectivity than the actual ground here, the pasture. And on the bottom, you have a range slice and an azimuth slice. So the range slice is this horizontal line here, just one azimuth line coordinate, and then a slice along this line through range, showing at each point here this the vertical profile that we would also see up here. And again, for azimuth slice, it's similar. Yeah? So that's the vertical line that you see here. And well, we can play around with it a bit. We can here use this slider to see different horizontal slices at different inversion heights. I'm going to stay with 0 for now. And you can use this range slider to adjust your plot. So you see it on the bottom here. We are interested only in this forest. So here to the right is the forest, and you also see it here. We're only interested in this. And so below it and above it, this blue area, well, there's not so much information and we want to blend it out. So we adjust our plot to only show us this area, to zoom in a little bit. And yeah, this is what you see here. And you can click on this horizontal plot repeatedly. And you see here the vertical profiles are stacked on top of each other. So you can directly compare them. Unless you check that box here, uncheck it, don't have the vertical plots stacked, and then you click again and it just shows you one of them. And you click repeatedly and refreshes the plot. So let's stack again. You can click through it, you see it stacked, and then you can also use this box here, click vertical, clear vertical plot, and you have a fresh start. So what do we see? Well, let's stay here for the moment. You see here, we take this range slice, so this horizontal line here, and well, there's not much to see in the pasture. It's just no height variations at all. And then we have this little peak here, the first peak. And this is actually this line of trees that we were mentioning earlier. So this line here. So we see we can depict the height of those trees here. And then we go further and have again the pasture, not much height variation. We don't see anything in the vertical profile or in the range slice here. But then just at about the middle of this line, the forest starts, and now we see something going on. So we have the reflectivity basically in this tomography result in this vertical profile going from the very top of the tree down to the ground. And you see that varies quite a bit. So sometimes the highest reflectivity is very up in the tree, in the crown of the tree. Sometimes there is gaps apparently in the crown, and you see here more of the undergrowth, any brushes that are underneath the forest. And yeah, well, you can take this result now and really explore actually the forest characteristics, the height and the volume and undergrowth of this particular forest with this SAR tomography result. Once we've done that now, we've done the analysis, we can do one more step, and that's the actual geocoding. As I said, the images are in slant range, it's radar geometry. We want to do it in the geographic geometry to also load it into our GIS system, explore it in this way. And for this we have two additional files. They are the lookup tables for converting the radar coordinates, actually the pixel coordinates, to geographic coordinates. So these two LUTs, They are geocoded, they are regular images, but the pixel image values are not any data. Well, they are just the radar coordinates. So each pixel contains the location in the image, in the geo image, and tells you what radar coordinate pixel-wise in range and azimuth would be in that pixel, in this geocoded pixel. And we are going to do this with the Kappan norm, with the normalization result of the Kappan beamforming. But the way we do it here, you could easily just do it with the SLC data as well. That works just as well. And one more thing, there's 4 other variables here, but you don't really need to worry about them. They are just subset variables, coordinates of this LUT that we have, because the whole data set that we have is a subset of a much larger data set. And so also the coordinates that we find in the LUT, they are linked to this large data set. So as we have here, the 0, 0 coordinate would then refer to, well, a different area in this larger data set compared to the small subset that we have here. So we need to subset this, and you can leave these coordinates just as they are. We do the geocoding, and this basically warps our radar coordinates or radar image into geo coordinates. So it rotates, flips, and also stretches a bit to have that geocoded. So we just use the lookup tables and we can display the result again. So that's basically a simplified version of the plot that we had here. So just a horizontal slice. But now we have different coordinates. We have easting and northing because it's an UTM projection. You can again use the slider up here to slide through these different horizontal slices. And also, let's jump to 0 because there's the highest contrast. Looking at this image and then comparing with Google, you see that's exactly the area that we're looking at. Yeah. So this image again, and then Google. So this edge here in the forest, you can clearly see it also here in the image. All right, that's it. All processing steps done. Head on over to EO College for contact details. You can send us suggestions for improvements, or maybe also contribute if you like. And well, thanks for your attention, and I hope you had fun with the tutorial, and even more fun by doing it yourself and maybe improving it. All right, see you later.